Okay, let's say we make an app note on the Bode plot application for the Rigol. I strongly suggest that you look at the MSCO 5000 Bode plot app note. It contains a lot of information, and it's also contains a color version of the same graphic that you see on the scope. But basically what you have is you want to protect the frequency generator, the signal coming out from the generator. It's only a 0 plus or minus 5, and the impedance output maybe it's 50 ohm. I'm not sure about that, but basically you want to protect this from the high voltage, high current that you could have with switching transformer. So you want to insulate your scope from that. You want to protect your scope. So how it works, usually you use a insulation transformer, or better called an injection transformer, that is designed for that. Those are very costly, but basically you inject your high impedance on this side, and on the other side you modify the signal for the normal switching transformer. There is a sense, and then sense goes back into the feedback loop, and the switching, depending on the frequency, 1 kHz or 10 kHz, but basically you have a very low impedance, very high voltage coming to that point, and you want to be insulated from that point. So to do this, you need the insulation transformer. If you look at the probe, you see a little bit of the way it's done. Here we got a professional insulation transformer. And by the way, you don't want to hook up your ground wire or shield from your probe to anything inside, because you are on the high voltage side over here. So if you look at the picture, you see that the ground clip are connected together. Only the sense goes into the high voltage switching power supply. This is a 5000 scope, but the same go for any scope that you want. So you need the insulation transformer. Those are the kind of insulation transformer that are used. Usually they cost a lot. You could, well, a lot meaning $300 to $1,000, depending on what you want to do. But a lot of people are building their own. It's basically simply a coil, something like that. You have to play with the material that you have, and there is a lot of picture and information on the network how to do that and how to test it. The nice one here is just very plastic small case with only a coil, and you want to insulate yourself from high voltage, so you cover it. For insulation transformer, you want either you buy those kind of professional thing, and it goes to frequency up to 1 megahertz frequency. For 1 meg, it's flat over there. But for regular switching power supply, I don't think you need to go too high. It's a few 100 kilohertz maximum, few 10 of kilohertz or on normal power supply. Again, depending on what you want to do. Here's another example. Basically, it's just a coil. You try to put high impedance on the scope side to protect it, and the other side is the low impedance. Here's other design. You see, well, that's the same kind of thing. So if you look at it, you want to build your own. It will be less costly. One thing you want to make sure is the frequency response of your transformer is flat to up to a point. At that point where the thing is non-linear, it's the point where the transformer will not be useful anymore. So you don't want to have any kind of panicking mode on the amplitude or the phase, and this is where you want to look at it. So in the past I was using this transformer. It's a small one. It's basically just a 320 ohm on the 110 volt. The output is something like 12 volt or something like that, with 6 ohm of DC resistance. And looking at it, I was only able to achieve 64 kilohertz, which is already good anyway. But I found a very old stock that was cluttering my storage since 1970 something. It's 600 ohm on this size and something like 41 ohm on the other size. And look at the frequency response of that thing. That's magical. Basically, you got a flat response from 10 hertz up to the first resonance frequency is where the amplitude on red goes high a little bit and then it goes low, but it does not panic too much. But basically the phase goes to the green, goes to 90 degrees. So it's a limit, I would say, for this transformer. But even though you look at it, it's only there that it's panicking, and it's not panicking by much. So it try to recuperate itself, and it goes on and on up to 25 meg. At 25 meg again, the frequency collapse at let's say 22, 21. But it's the phase do not goes all around the place. It stays around 0 except for the small peak at the frequency. If I put the cursor there, this is probably the maximum that you want. But it's 90 degree phase, but it recover very fast after that first resonance. So it's still useful beyond that a little bit. The amplitude is the red line is staying around the same gain from the beginning, so it's not too bad. So basically, you could work up to 260 kilohertz with this transformer. And again, this is a very old transformer, and it's a very nice one. Well, it's now a dark brown. I just found equivalent on eBay for 10 bucks. It's a vintage. Here the PCI is the brand with the model number, and while this one is white, I'm not sure if the plastic is different, but whatever. This one was a little bit less dark than it was when I remember it very long time ago. I don't remember exactly what it was used for, but it will do the trick for me. So basically, when you use this for the response of a Bode plot response of a switching power supply, you want to have high impedance injection of your frequency generator on the 110 volt, and the low impedance output that you collect in parallel with the 5 or 10 ohm that you modify on your circuit of your switching power supply on the other side. So that protects from the DC, that protects from the low impedance of the switching, so the switching signal do not goes up to the other side because of the difference in the impedance. But it's a very nice circuit. And I was using this Bode plot function. It takes long time. I was not sure about the if there anything as a frequency response, so I put the maximum sampling point to, let's click on here to make this measurement, 300 points. So that's a maximum, 10 to 25 megahertz, which is maximum, and the amplitude also is maximum to 5 volt on the frequency generator. And it took something like 20 minutes to do all the measurement, but it was able to achieve it, and I'm very pleased with the results. Bye.